Good afternoon. Myself, Dr. Abdul Hakkim VM, Professor and Head, Department of Soil and Water Conservation Engineering, Kerala Agricultural University. I am presenting a paper on effect of soil tillage on soil physical properties in laterite soils as part of the 4th International Virtual Multidisciplinary Conference on Viksit Bharat 2047. Coming to the introduction of my topic, in modern agriculture, tillage plays a crucial role in preparation of the soil for planting crops. Tillage is mechanical manipulation of soil to provide a favorable condition for the crop growth. So the major objectives of tillage are to obtain a deep seed bed suitable for different types of crops. A granular structure is desirable to allow rapid infiltration rate and to control weeds and to minimize the erosion by following such practices as contour tillage, listing or proper placement. And tillage can be broadly classified into primary tillage and secondary tillage. Any operation performed to open up the soil, that is primary tillage. Generally moldboard plow, chisel plow or rotavators are used. And secondary tillage is the lighter and finer operations performed after primary tillage. So very little invasion of soil takes place, and the implements used are disc plows, cultivators, sweeps, etc. In the present study, 20 plots are selected with 4 treatments called treatment 1 primary tillage, treatment 2 secondary tillage, treatment 3 primary tillage and secondary tillage, and treatment 4 no tillage. The particle size distribution, soil moisture content and bulk density, particle density, soil hydraulic conductivity, infiltration rate and the soil pH were determined to determine the effect of tillage. The objectives of the study are to evaluate the effect of tillage operations on moisture content, bulk density, porosity, particle density, saturated hydraulic conductivity, infiltration and pH of the laterite soil. Coming to the review of literature, Martinez et al. In 2008 reported that no tillage system affects the soil properties depending upon the soil climate and the time since its implementation. In heavy and no-till soils, surface compacted soil are commonly found. Such layers can affect the root growth. And Amami et al. In 2021 reported that moldboard ploughing enhanced the soil infiltration capacity relative to no-tillage. Coming to the materials and methodology, the 20 plots were selected with 5 replications of 4 treatments. The first treatment being primary tillage, second treatment secondary tillage, and third treatment primary and secondary, and fourth no-tillage. So 4 treatments with 5 replications, altogether 20 plots. The primary tillage ploughing was done with the help of a moldboard plough and 2-bottom MB plough was used. In the secondary tillage, it was done with the help of a tractor-mounted harrow, power harrow. And the primary and secondary tillage together, the primary tillage was involved with moldboard plough and secondary tillage was performed with the help of tractor-mounted harrow. So initial ploughing was done using the moldboard plough. One day after the secondary tillage, using the harrow was done. Both operations were restricted to 15 to 30 centimeters. In the no-tillage, vegetation on the plats were removed manually. Now data analysis, it refers to the range of size of particle size. The particle size distribution is the first parameter, range of size of particle. It was done with the help of sieve analysis using different sieves of 2 mm, 1 mm, 600 micron, 425 micron, 300 micron, 150 micron, 75 micron. Then second parameter, the soil was oven dried and half kg of the soil was used, and then it was placed in the bottom tray of the sieve analyzer, and the sieve shaker was used, and the percentage written in different sieves were analyzed. And second parameter is soil bulk density with the help of a core cutter meter, which is the most common device used for determining bulk density. It is calculated by dry weight of the soil divided by total volume. The volume includes volume of solid as well as volume of voids. Now coming to saturated hydraulic conductivity, it was done with the help of a concentrated permeometer. Soil specimen was prepared and kept below the permeometer, and the analysis was done with the help of concentrate technique. The infiltration rate of the soil was measured with the help of a double ring infiltrometer, means 2 concentric cylinders of 15 and 30 centimeters, and the rings were driven into the soil to a depth of 10 centimeters with the help of a hammer. Coming to the pH of the soil was analyzed using pH meter. The soil pH for 10 gram of the soil sample were taken and 20 ml distilled water was added to that, and it was kept for 15 minutes. After then it was kept and undisturbed for 30 minutes, and again stirred and pH was noted. Coming to the results and discussion, moisture content was calculated using the oven dry method. A graph was plotted to show the variation of moisture content with x-axis replication and y-axis moisture content. Primary and secondary tillage together resulted in the highest moisture content. And then bulk density, a graph was plotted with x-axis and treatments and y-axis moisture bulk density on x-axis and treatments on y-axis. Bulk density was more in the case of no-till condition with 1.773 grams per cc. Bulk density all soils decreased with increase in the porosity. It is clear that the present study, bulk density decreased with tillage in the order of T4 greater than T2 greater than T1 greater than T3. Coming to the particle density, a graph was plotted showing particle density on x-axis and treatments on y-axis. Graph shows that particle density was almost same for all treatments, hence it can be concluded that there is no change in the particle density due to tillage operation. Coming to the porosity, porosity was calculated from the particle density and bulk density. A graph was plotted on x-axis replication and y-axis porosity. The graph shows that the porosity got increased with tillage. Porosity was more for treatment T3 while bulk density was very less for this treatment. Coming to the hydraulic conductivity was measured using the consonant per meter. A graph was plotted and it was from the graph it is clear that the treatment 3 has more hydraulic conductivity and about 49.12 centimeter per day. In the hydraulic conductivity values were in the order of T3 greater than T1 greater than T2 greater than T4. The infiltration rates were plotted and the infiltration, the accumulated infiltration equation was y equal to 1.973 e raised to 0.2270. In the infiltration for the secondary tillage, the equation was 0.863 e raised to 0.24960. And the infiltration equation for the third treatment, primary and secondary tillage together, the y is equal to 2.23 8 e raised to 0.25 t. And for no tillage, the functional relation was y is equal to 1.5419 e raised to 0.218 t. Soil pH was measured using the pH meter. It was observed that the pH of the soil was not affected by the tillage as the process is only a mechanical manipulation. pH was noted between 5.5 to 6. This is statistical analysis was done with table 1 ANOVA table of moisture content, table 2 ANOVA of table bulk density, and third table is ANOVA of particle density, then ANOVA of porosity. Here in all cases it rejects H0, where H0 is there is no significant difference between the treatments. Coming to the summary and conclusion, tillage operations in the mechanical manipulation of soil to develop a desirable soil structure for seed bed and to establish a specific surface configuration for planting, irrigation, drainage and harvesting operation, etc. The study was aimed to assess the variation of the properties such as moisture content, bulk density, particle density, porosity, saturated hydraulic conductivity and pH and infiltration rate on due to tillage. The average moisture content of the soil increased with the order of no tillage, secondary tillage, primary tillage and primary and secondary tillage together. The bulk density of soil reduced with tillage because it increased with the void ratio, and particle density remained constant because tillage and other short-term changes to the will not alter the amount of chemical composition in the mineral particles. Coming to the porosity increased in the order of no tillage, primary tillage, secondary tillage, primary and secondary tillage together. Tillage practices highly influence the saturated hydraulic conductivity of the soil. The saturated hydraulic conductivity was increased with the order of no tillage, secondary tillage, primary tillage and primary tillage, secondary tillage together. Infiltration rate was increased with the tillage because the increase in porosity. Increase in infiltration rate with the tillage was the order of no tillage, secondary tillage, primary and secondary together. pH was found to be unaltered, and tillage practices improved the overall physical properties of the soil. And these are the references, and thank you.
Namaste to everyone. Myself, Dr. Munmi Borah. I congratulate the team for organizing such kind of online conference for the benefit of the scientists and the researchers. So, the first paper in this session was presented by Dr. Abdul Hakkim PM on effect of tillage on soil physical properties in laterite soil, and his objective was to obtain deep seedbed with granular structure for different crops, and his results indicated that the order of soil moisture increasing were no tillage, secondary tillage and primary tillage, and finally the combination treatment. I congratulate Dr. Hakkim for his excellent research work.
Namaste for everyone. I am Sridhar Gannavaram. Today I will be presenting our work titled Smart Weather Alert System for Farmers, which focuses on automated SMS alert systems, voice-based notifications, and AI-driven advisory to improve agriculture resilience. The motivation behind this work is farmers are increasingly vulnerable to climate variability. Yet timely and actionable information is still not reaching them effectively. Agriculture today is facing unprecedented challenges due to climate variability. Weather patterns have become highly unpredictable, directly affecting crop yield, irrigation planning, and resource utilization. One major issue is that farmers often depend on generic weather forecasts, which do not reflect conditions at the local or farm level. What farmers truly need is real-time localized weather intelligence that help them make immediate and informed decisions. Our system is designed to bridge this gap using digital communication and AI-based advisory support. When we analyzed existing weather alert systems, we identified three major gaps. First, weather alerts are often delayed, reaching farmers after the damage has already occurred. Second, most systems provide raw weather data but not actionable guidance. Farmers need to know what actions to take, not just what their temperatures or rainfall will be. Third, there are serious accessibility barriers. Language diversity and literacy limitations make many digital platforms effectively or rural communities. This gap significantly reduces the practical value of existing solutions. Our study highlights a clear research gap. Current solutions are fragmented, which separate systems for weather data, alerts, and advisories. Voice-based alert systems, which are crucially for low literacy users, are still very limited. Additionally, most advisories lack of local and crop-specific context, resulting in generalized recommendations that may not suit individual farms. This motivated us to design undefined, accessible, and intelligent systems threshold specific for farmers. Based on these gaps, we defined four key objectives. First, to enable real-time weather monitoring using reliable external APIs. Second, to implement automatic detection of extreme weather data such as heat waves, storms, and force throws dynamic thresholds. Third, to ensure instant alert delivery via SMS and automated calls. Finally, to provide AI-based and multilingual farming advisories, offering simple and actionable guidance tailored to local conditions. To achieve these objectives, we propose an integrated alert and advisory platform. Unlike existing systems, our approach combines weather monitoring, event detection, and alert submissions and AI-driven advisories into a single cohesive solution. The system is designed with a farmer-first approach, featuring simplicity, accessibility, and reliability even for users with a minimal digital exposure. The system implementation follows a three-stage pipeline. First, real-time weather data is continuously collected using Open Weather API, and second, event-driven logic layer analyzes this data against predefined and adaptive thresholds to detect potential risks. Finally, once a risk is identified, alerts and AI generate advisories are instantly delivered SMS and automated calls, ensuring timely and widespread communications. The impact of the system is significant. Farmers are empowered to make timely decisions, reducing crop damage and optimizing resource. Voice alerts and multilingual supports dynamically improved accessibility, and especially for rural and low literacy communities. Additionally, the system is scalable and cost effective, making it suitable for deployment across diverse agriculture regions. In conclusion, our smart weather alert system directly addresses critical challenges posed by climate variability in agriculture. By delivering timely, actionable, and accessible information, the system significantly enhances farmers' preparedness and resilience. We believe this approach can play an important role in supporting sustainability agriculture and improve farmer livelihood. Thank you for your time and attention. We look forward to your questions and feedback.
The second paper was on design and implementation of an automated weather alert advisory system for the farmers by Sridhar Gannavaram. I congratulate Dr. Gannavaram for his outstanding research work on developing a smart weather alert system and AI-based advisory services for the farmers. Definitely, this will be very much useful for the farming community. The third paper.
So good day everyone. Today I am presenting the research entitled Evaluation of Moringa Genotypes for Leaf Yield and Quality. which was conducted at Kumaraguru Institute of Agriculture, which is situated at Eeroor. The study focuses mainly on accessing the 13 Moringa genotypes for identifying the best performing accessions for especially for the leaf yield and nutritional quality. Next, coming to the main crop that I was chosen for this research should be Moringa oleifera, which is often called as miracle tree, which is a highly nutritious plant which will have the higher bioactive components. Coming to the objective of this study will be about to evaluate 13 different Moringa genotypes for the growth and leaf yield, and also to access the biochemical parameters or qualities such as the vitamin C, carotenoids, moisture content, and also chlorophyll levels that will be present in the 13 different accessions of germplasm, and also to identify the superior genotypes for further hybridization and commercial cultivation. Coming to the materials and methods, I have chosen 13 different genotypes that will be collected from the different locations of the Tamil Nadu. The field experiment was laid out in RBD design under the 3 replications in the field condition. Next, the study evaluated the plant height, number of branches and primary and secondary branches, number of leaflets per acres, leaf area, leaf yield per plant, vitamin C, carotenoid, moisture, chlorophylls, especially the chlorophyll level which was obtained by using the speed meter. And then coming to the growth performance among all the genotypes studied, T12, that is an Andiur Pachapalayam local, recorded the highest plant height. It also excelled in a number of leaflets, parameters like number of leaflets, primary branches and secondary branches and all. And then coming to the physiological parameters, recorded best in T3, Kilwan in local, recorded the highest chlorophyll content and photosynthetic efficiency. And then coming to the leaf yield, the highest leaf yield was obtained in T12, that is an Andiu Pachampalayam local, which was followed by T3 and T6. And then these genotypes were conferred as a superior quality in case of leaf area, higher leaflet numbers and better branching patterns. Coming to the biochemical characteristics, T3 performs well, which will have the highest vitamin C content, and also T6 will have T carotenoid, highest carotenoid content, and T1 Coimbatore local records higher moisture content. And then coming to the key findings of this research should be about the multiple growth and biochemical parameters revealed the significant variations occurred across various genotypes. Among the genotypes analyzed, T12 and T3 and T6 will consistently performed better across multiple growth and biochemical parameters. Coming to the conclusion, among the various genotype studied, T12, T3, T6 emerged the most promising performance for the leaf yield and quality. This preliminary evaluation provides the baseline for data for selecting further Moringa genotypes for that will be used for the large scale cultivation, nutritional enhancement programs, and also for the development of hybrid and also for maintaining the Moringa genetic germplasms. And finally, I thank Kumaraguru Institute of Agriculture for providing the facilities, research support, and Moringa Genetic Resource Garden that made this study possible. Thank you all.
The third paper was presented on evaluation of Moringa genotypes for leaf yield and quality by Dr. Mrs.P.Bhavithra, and they have evaluated 13 Moringa genotypes for their suitable traits of high yield, and they found 3 genotypes were very significant in their yield, which can be utilized further. I congratulate to the team.
Good morning, ma'am. We are here to present our paper titled Smart Weight and Monitoring System for Agriculture Transaction. Our project group include Aniket Mathure, Aniket Gangade, and Vedant Majan under the guidance of Dr.Vaishali Baste ma'am. This work is being done as a part of our BE in Electronics and Telecommunication at Srimati Kashibai Navle College of Engineering, Pune. Now we are towards the main presentation of our project, starting from introduction. In traditional agriculture trading, weighting is often manual and can be inaccurate. Dispute between farmer and businessman are common because there is no reliable proof on the actual weight. Our purpose system providing a digital and transparent solution that automate the weighting process. Here, the ESP32 cam act as the main controller, capture an image and reading weight data. All this information is securely stored on Firebase. Both parties can then access it in the form of mobile app, ensuring no manipulation and full transparency. Now, objective. First, to design and build a system that accurately measure the weight of the grain bag using a load cell. Second, to capture or record a digital image of weight objective using ESP32 cam. The third objective of our system to display the weight data locally on the OLED display for implement verification. Fourth, to transmit a collected data, image and weight to secure cloud-based database, that is Google Firebase. Fifth, to create a mobile application for both farmer and a businessman to access transaction record, view digital proof and perform automatic calculation, that is total weight and price profit loss. Out of these 5 objectives, we completed 3 objectives, that is objective number 1, 3rd and 5th. Still we completed objective number 2 and 4th, still incomplete or pending. In short, we can say that around 60% of work is done, including the hardware prototype and basic mobile app UI. Now, literature survey. We studied around 9 research papers. Out of that, first is the most advanced and most updated research paper, that is IoT-based digital weight scale in rice inventory for MSME. This research paper focus on a businessman, not transparency between farmer and businessman. There is no visual proof, limited mobile access. And second research paper is ESP32 with load cell and HX711. It is a basic digital weighting machine. There is no data storage or image proof. On this line, we have studied 9 research paper. We can conclude in that most systems focus on either weight measuring or environment monitoring, but lack visual verification and secure cloud login. But our project combines these 3 aspects: weight, image and cloud in one system. These slides show the complete working of our system. When switch 1 is pressed, a form open on a businessman dashboard. Its form, the businessman enter the farmer name, mobile number, and the trade and essential information there. The mobile number is a unique ID for the farmer. Once this information is sent from dashboard, a short confirmation message appear on a OLED display for few seconds. After that, the load cell becoming active and is ready to measure the weight. When switch 2 is pressed, the load cell experience force of the grain bag and convert into analog signal. The signal is very small, so amplifier using an HX711 amplifier module which convert the analog signal into digital signal. This digital data is then transferred to ESP32 cam. Now ESP32 cam act as a main controller of the project. It has multiple GPIO pins used for interfacing peripheral like OLED cell, load cell, OLED display, buzzer and switches. It also has inbuilt 2 megapixel camera, that is OV2640 camera module that capture image of weighting grain bag for record purpose. The ESP32 cam has 32 dual core processor, Wi-Fi support, built-in flash memory, which make it ideal for IoT based application. Once ESP32 cam receive the weighting data, it perform 2 tasks simultaneously. First, it display the weighting data on OLED display, and second work is it transport the data at Google Firebase. Also, image also transferred. The data stored on a Firebase can then be accessed through the software application, which has 2 separate interface. One of the businessman, another of the farmer. One of the businessman dashboard, all farmer transaction detail are available, including bag image or weight, total number of purchase, profit and loss analytics, pending and paid amount, other analytics data related to business activity. Although all information is calculated by software only from weight to price. On the other hand, farmer dashboard, the farmer log in using the mobile number which act as his ID. Hence, he can view all transaction with a particular businessman, including bag image and weight, the history of all bags, the amount of already received, the pending amount, and all related transaction detail. This system thus ensure complete transparency and digital record keeping for both parties. The businessman can analyze this trading activity while the farmer can verify every transaction made with accurate proof. Now advantage. Trust and transparency. Reduce human error. As you decrease manual work, so we can minimize the human errors. Fraud prevention. As you all data is sending cloudly, so no manipulation of data is done there, so we can say the fraud prevention. As we created two dashboard separately for a businessman and farmer, so we can say it is a high accessibility and effectiveness, although weight to price is calculated automatically without any intervention of businessman or anyone. Applications. Agriculture market like FMC and government market, small warehouse and local traders, parcel and logistic verification system. To conclude, our smart weight and monitoring system provide low cost, reliable, transparent method for agriculture transfer. All through cloud and full mobile app integration are pending. The current prototype successfully read and display weight and capture image using ESP32 CAM. In the next phase, we will connect to Firebase and fully automatic data login and app synchronization. It is our hardware image. This includes ESP32 CAM, OLED display, two switches, load cell with the amplifier that is HX711. It is schematic of our PCB. It's 3D view of PCB. It is a short video clip in which we are trying to showing how data transfer from ESP32 CAM to Google Firebase. Here the word Sachin we are transferring to Google Firebase. It is a Google Firebase environment, real-time database. Repeatedly, we are sending word Vedant to Google Firebase. Now it is a screenshot of our application which is created by Flutter, using Flutter. Thank you, ma'am, for your attention. We are welcoming your any question and suggestion.
The fourth paper presented by a group of students on smart weighing and monitoring system for agricultural transaction using ESP32 CAM and load cell. And their aim was to design a prototype of a smart weighing monitoring system, and this will be definitely utilized by the farmers. So thank you Vedant Knowledge System for giving me this opportunity to go through this beautiful research works. And once again, I congratulate all the participants who presented in this session. Thank you and namaste.